Okay, I think we can start now. So good morning, everybody. So what is left here in this chapter, in this chapter is actually two definitions. One is about delay. The other one is about bandwidth delay product. I have already explained this delay before in chapter 1. So as you know, when you transmit a message, the message is going to take some time until it is delivered. Okay. And there are several reasons of this delay, as I explained before. One reason is actually the propagation time, propagation delay. For the signal itself to move from one point to another is going to take some time. Also, transmission delay. Okay. We have the queuing delay. So the signal has to stay in the queue for some time if there are congestion or if the traffic is busy. So as I told you before, every router has something like a queue, and if it receives too many packets, it's gonna store. It has to keep these packets in the queue for some time. Okay. Also, we have one more reason for the delay. That's what I explained in chapter 1, processing delay. Okay. As you know, if we have a router, after the router receives the message, it has to look at the address, and then it has to decide either this packet has to go here or to go here. You got what I'm saying? So this is processing delay. Because of this whole delays, as I told you, when you transmit a message, the message is going to be delivered after some time. For sure, the lower the time is better, that's for sure. Okay. So let's talk about two delays here. One here is the transmission delay. So the transmission delay actually is the message size. How big is the message divided the bandwidth of the channel? Okay. So you can tell here the bigger the message, the size of the message. So actually the transmission delay is going to take more time. Also bandwidth. The lower the bandwidth, the higher the transmission time. So as you see here, the bigger the message, the longer the transmission time, lower bandwidth means bigger transmission time. Okay. So, and I have a good, I have numerical example here to compare between transmission and propagation time. For propagation time, I told you it takes some time for the signal to move from one point to another. So actually the propagation delay here, propagation time is actually, this is one related to the distance. How big is the cable? Okay. So propagation time is the distance divided by the propagation speed. Okay. So as you know before, any time should equal distance divided by speed. Or it's the same thing if I say speed should equal distance divided by time. It's exactly the same thing here. Okay. So here, so again, the propagation time depends on the distance and the propagation speed of the cable. But the transmission time depends on how big is the message and also the bandwidth. So I want to give you two examples, numerical examples to better understand these two delays. Let's start with the propagation time. Okay, we assume here we have a very long cable. This cable is actually 12,000 kilometers. You can imagine how big it is. 12,000 kilometers. So it's a very long cable. We assume that this is a propagation delay. So if you have this very long cable, if you transmit a signal here, how much time is going to take for the signal to reach to the end of this to get delivered or to move from the beginning to the end? Okay. So actually, as you see here, propagation time is the distance. This is the distance. It's exactly the same distance here, but all what I did, I just convert it to meter instead of kilometer. Okay. And this is the propagation delay. This is, sorry, the speed. It's also meter per second. So if I do the calculation, it's going to take 50 milliseconds. This number is very interesting because you can see how fast these signals are. If you have 12,000 kilometers, you can imagine how big it is. 12,000 kilometers. Okay. It's a very huge cable. The signal only needs 50 milliseconds to move from the beginning to the end. So they are really very fast. Okay. So this is a propagation time. For the same example here, I'm going to talk about, so the same example, but here I want to talk about the transmission time. Okay. So here I'm telling you, it's exactly the same example. It's the same cable here, as you see. it is the same. Yeah, it's the same cable. Okay, it's the same speed. That's why propagation time is 15 meters. And now let's talk about the transmission time here. Assuming I want to transmit 2.5 kilobyte message, and this is the bandwidth I have. Okay, so the message is a small message, and the bandwidth is a huge bandwidth. So you should guess, before even we do the calculation, you should guess the transmission time should be too small. Too small, okay? Because a small message divided by a big bandwidth, okay? And that's exactly what happens. So if I do the calculation, so this is the message. This message I have to convert to bits. So it's 2.5. So actually, this one is actually 2.5. Because of the kilo, I have to multiply by 1,000. And because it's a byte, I have to multiply by 8 to convert it to bits. Why you have to convert it to bits? Because actually, this one is bits. So, okay, so both of them should be bits. So anyway, if you do the calculation, you can see here, actually the transmission time is very small. Actually, in this case, I can actually ignore the transmission time because the propagation time is much bigger, is dominating. So if you can even, if you want to calculate the total delay, I can actually ignore this one because it's small, okay? This is just one scenario. I'm gonna repeat the same example again, but I'm gonna give you another scenario. In this scenario, the message is gonna be big. I'm gonna make the message big. Also, I'm gonna make the bandwidth small. I'm gonna make the bandwidth small. Okay. So you will see this one is gonna jump from this number to a bigger number. Okay. So that's exactly what I did. So what I did here, the message, I'm gonna make it big, like 5 megabytes. Also, I'm going to make the bandwidth very small. Instead of 1 giga, it's going to be 1 mega. Okay. As you know, we have 1 kilo, which is 10 to the power 3. We have 1 mega, 10 to the power 6. We have 1 giga, which is 10 to the power 9. Anyway, so if I do the calculation, as you see here, this is the message. This is the bandwidth I have. So in this time, look how it jumped almost from 0 millisecond to 40 seconds. Look how it jumped to 40 seconds. You got what I'm saying? In this scenario, if I want to calculate the total delay, I can actually ignore the propagation time because it's much shorter than the transmission time. So before I take this question, I'm going to tell you the conclusion. What I want to say here is we have propagation time, we have transmission time, okay? I give you two numerical examples. In one example, I give you a message was a small message, and the bandwidth was two big bandwidths. That's why the transmission time was very small. In the other example here, I made the message very long, and actually I made the bandwidth we have here I made it like very small. That's why you can see the delay is huge delay. Yes, what's your question? I'm not hearing you. Okay, because yeah, so this one megabit per second, bit per second, bit, not byte. So because this one bits, this one also has to be bits. If this one bytes, this one would be byte. So they have to be the same. You got what I'm saying? So because this one bit per second, so this one I have to convert to bits. Okay? Because this one is gonna transmit 1 million bit in 1 second. So if you want to calculate time, I need to know how many bits you are gonna transmit. That's why you need to convert to 1 bits. Any questions?
Transmission is like transferring data from A to B, but what about from B?
No, propagation means if you have a cable, okay, if I send the signal itself is going to take some time to move from point A to point B. You got what I'm saying? This is a propagation. The other one here, the transmission, is related to how many bits you can transmit per second. You got what I'm saying? It has nothing to do with the movement of the signal. You got what I'm saying? Because there is a limit. I cannot, if I have a message 5 megabit per second, I cannot transmit it in 0 second. Okay? There is a certain bandwidth I have. Because of this bandwidth, I can only transmit 1 mega every 1 mega in 1 second. 1 megabit in 1 second. This can create a delay. So if I have 1 megabit, I need 1 second to transmit it. It's not gonna be 0 second. You got what I'm saying? So anyway. The last thing here I want to define in this chapter before I move to the next chapter is about something we call it bandwidth, and something bandwidth delay product. So you can tell from the English name what we are going to do here. I'm going to multiply the bandwidth by the delay. You get what I'm saying? So first of all, so here you are going to multiply bandwidth by delay. Okay. So number one, what is the unit of this one? This number one. Number two, what this means? What this metric? What this metric means? When it gets bigger, is it better? If it is small, it's better. What this means? Okay, that's what I'm going to explain now. Let's start with the unit. So what is the unit of this one? Okay, very simple. So actually here, the bandwidth is actually bit per second. So how many bits per second, per time? Second, minute, whatever, per time. It's usually bit per second for sure. Okay. The delay is actually time. So when I multiply bandwidth, which is bit per time times time, so actually the result is going to be bits, number of bits. Make sense? This is unit. I'm talking about unit. I didn't talk about the meaning yet. I'm talking about unit. So if I multiply the bandwidth by the delay, the result is number of bits. 5 bits, 6 bits, 7, 8 bits, whatever it is. You understand what I'm saying? So this is as a unit. So now let's talk about the meaning. So what this means, I'm going to tell you what it means. Okay. So look at the main idea here. So actually, this means the number of bits that can fill the link, Okay. So for example, let's see this example to understand better what I want to say. Assuming the bandwidth is 1 bit per second, assuming the delay is 5 seconds, if I multiply them together, I'm going to get 5 bits. So what 5 bits means? It means the cable can have 5 bits in transition. I can 5 bits at the same time with the cable in transition. You understand what I'm saying? So what happens after 1 more second, this one is going to get delivered, and then I'm going to insert a new one. So you can think it's like a pipe. This pipe, I'm going to insert some bits. Okay. So at the same time, there may be 5, in this example, specific example, 5 bits at the same time with the cable. You got what I'm saying? So here, so this is the meaning of it. Okay, so how we are gonna use it? So something like that is that how it can be useful. I'm gonna tell you how. Okay, listen to me. The idea is that when you transmit messages, usually as we will see in one chapter in this course, I'm gonna wait for acknowledgement. Okay, so sorry, before I move to this one, I want to tell you something important. The main point here, I wanna fully utilize the cable, fully utilize the cable. You understand what I'm saying? So if I transmit only 4, so I didn't fully utilize it. So I wanna fully utilize the cable. This is the most important thing. Okay. So how? So number one, the metric is the multiplication of delay bandwidth by delay. This is number one. Number two, you know the unit is bits, number of bits. Okay. Number three, you know the meaning of it. How many bits can be in transition here? In transition. Okay. Or at the same time in the keyboard. Okay. So how something like this can be useful? I'm going to tell you how it can be useful. Okay, as you will see later in this course, usually when you send a message, you need to receive acknowledgement to send more messages. Okay, to send more message, I need to receive acknowledgement on the other side to tell me I received this message. Please send more messages. What I'm saying? No, yes, this can be in the TCP. Also, it can be on the second layer as well. So it can be the 2 layers. In the third, in layer number 4, okay, and also it is in layer number 2 as well. And this course we're going to teach in layer number 2. Okay. So here, what happens here, we're gonna set we send the data in person. Person means I'm gonna send some messages before I receive acknowledgement. You got what I'm saying? So why this metric is important? Because this metric can tell me how much message I can send or how much data I can send before I receive acknowledgement, and I can fully utilize the cable. Okay. So in this case, because once you transmit a message here, okay, and then after the receiver is going to receive the message, the receiver is going to respond to acknowledgement. You got what I'm saying? So how much time is going to take? It's going to take 5 seconds this way, and also another 5 seconds this way. Okay. So that means in order to fully utilize the cable, usually what we do, this is a burst size. So it's going to be actually double, 2 times bandwidth delay product. Okay. This is actually the time for the signal here for after I receive this bit, okay, for this bit to deliver. And this one is going to transmit acknowledgement back to me. This is the whole time. It's going to be double to go and come back. That means, listen to me what I when I say. So the importance of this metric is going to tell me how much data I have to transmit before I receive acknowledgement. You got what I'm saying? So here it is usually 2 times bandwidth. So in this scenario, I should transmit. So here in this scenario, I should transmit 10 here, 5, as you see 5 here. So here in this case, I have to transmit 10 bits before I should. So here the first bit here, I should receive the acknowledgement after I transmit the 10 bits. You got what I'm saying? Because again, if I transmit a bit now, it's going to take 5 seconds to get delivered. And then there is another 5 seconds to receive the acknowledge here. Okay. Again, the main idea here, this is the key point. I want to fully utilize the cable. So I want the cable to be busy all the time. You got what I'm saying? This is the main point here. So I think I give you another example here. So I can say this is actually the maximum amount of unacknowledged data for the full use of the link capacity. So again, I just change the number. I give you another example here. Here I'm assuming we have here 5 bit per second. Okay. So in this case, and here we'll transmit. So that means, as you see here, every second we're going to transmit 5 bits. Okay. So for a delay of 5 seconds, so it's going to be actually 25 bits. So as you see here, so that means if I multiply the bandwidth by the delay, this multiplication is going to give me how much data I can keep. I can be at the same time, or I can be in transition on the cable. So in this case, actually it's 25 bits. Also, this one can tell me I can transmit up to double this number, which is 50 bits before I receive the acknowledgement of the first bit. So the first bit here, I can, in order to keep using the cable. This is the most important thing. Any questions? Anyway, I think later, when I explain data link layer, you will understand this concept better. You will understand I need to transmit some data before I receive acknowledgement. You got what I'm saying? I'm going to receive acknowledgement for the first byte or first data I sent. Okay, so let me, for example, here in this case, you are going to transmit here. You are going to transmit here 25. So I'm going to transmit actually here 50. So the acknowledgement I'm going to receive here, which is going to be acknowledgement for the first one here. You get what I'm saying? Because once you transmit it, it's going to take double the time until I receive acknowledgement for this one. Any questions? Anyway, it's going to be clear later. Just take it now as a metric, how we calculate it. What is the unit of this one? How it can be useful. But I'm going to give you more details later. But this can be useful to tell me how much data I have to transmit before I receive acknowledgement. Okay. Any questions? Now we're going to move to next chapter. So I want to before I start this chapter, I want to tell you what we're going to do in this chapter and next chapter, and how this is related to what I explained before. Okay. Okay. So I explained before we have something like baseband transmission. Okay. I told you in case of baseband transmission, we're gonna transmit a square wave as a square wave this way. Okay. And then if you have a cable, and no sharing. I'm not going to share the cable. If there is a cable, I'm going to use the cable all the time. Okay, that's what I told you. Okay, and I told you here, I don't need to convert this signal to analog. So if I want to just transmit, I'm going to transmit it this way. I told you we have a problem here. What is the problem? The problem is this one actually has infinity frequencies, infinity, because this rapid change here. So if you look at the time, if you look at the frequency domain of this one, it's going to look like something like that. So it has frequencies until infinity. You got what I'm saying? What is the problem here? The problem is this cable. I don't have a cable that can transmit this huge frequencies. It can't. You got what I'm saying? So this is the problem. But this is the bad news. I told you the good news is I don't need to transmit all these frequencies, because actually, and this is one of the beauty of the frequency domain. Frequency domain can tell you how many frequencies we have. What is the importance of every frequency? You got what I'm saying? So if I look at this frequency domain, I can see I have frequencies from 0 until infinity. I can see that. However, also I can see these frequencies are not important. Okay, these frequencies are not important because the amplitude is very small. So that's what I told you. So what I told you, when you transmit this one this way, we can actually ignore some of these frequencies. It's going to be distorted a little bit, but should be okay. You got what I'm saying? So this is baseband transmission. This is actually what I'm going to explain in this chapter. So in this chapter here, this is chapter 3 in this course, with chapter 4 in the textbook. So this chapter, you can tell from the English name, digital transmission. So this chapter is about this case. How can we transmit data? When I say data, for sure you know, I mean data here means 0 or 1s. How to transmit these 0 or 1s using digital signal, okay, or discrete signal, as you will see. The other case, and that's what I'm going to teach in the next chapter, we called it broadband. The idea of broadband is if you have a frequency, okay, we can share the medium. It's like in the air, as I told you, in the air. So in the air, we can use Wi-Fi, we can use Bluetooth, we can use 4G or 5G, all of them happening at the same time. You know how we can do that? What we do, actually, we divide the frequency. So here, every transmission has a certain frequency band. You got what I'm saying? As long as you transmit in different bands, you are okay. The problem happens when you two devices transmit with the same frequency. This is a problem. You got what I'm saying? But as long as we have different frequencies, should be okay. Okay. So now the problem is, and this is the interesting part, that's what you are going to understand in the next chapter. If I have, for example, voice. In case of voice, usually the bandwidth, I think it's between 4 kilohertz, or sometimes it reaches to, I think, from 0 until 20 kilohertz. You got what I'm saying? So if I have a certain signal, okay, so how the same signal I can transmit in this band, or the same signal I can transmit in this band, or the same signal I can transmit in this band. You got what I'm saying? The same range of frequencies. I can put it in this band, in this band, in this band. As you will see later, the way you are going to do it, I have to use what we call carrier frequency. You got what I'm saying? So here we have a carrier frequency, you have carrier frequency, you have to carrier frequency, and so on. So the same frequency or the same signal, I can put it in different bands. Okay. Anyway, so in this case we need modulation and demodulation. And so here in this case, we're going to transmit analog signal, and our data is actually carried by the analog signal, which we call it carrier. That's why we call it carrier. Okay. Anyway, so that's what we're going to do in this chapter and next chapter. So this chapter, I'm going to focus only in one thing. I'm going to focus about digital transmission. Okay. So if you have digital data, I'm not going to convert it to analog. You're not going to see any analog signal here in this chapter. We're going to only talk about this case, baseband transmission, which is how can you transfer digital. That's why you call it here, look here, digital to digital conversion. So what this means, digital to digital, I mean, this is digital data. Here, I mean digital signal. Okay, so you need to convert the digital data to digital signal. Okay, so anyway, I'm gonna give you the details. So here actually, here in this chapter, I'm gonna explain 3 different techniques. I think in network one, you got some idea about some of these techniques, but anyway, so number 1 here, I'm gonna explain what we call line coding. Line coding, this is essential. So we have to use it all the time. Okay. Also, I'm gonna talk about block coding or scrambling. As you will see later, this is something can be complementary to line coding. So this is something I can add it to the line coding to improve it, but it's not essential, as you will see later. Okay. But anyway, so let's go to the details here. So let's start with, so what we have to do here, look here. That's what we need to do. Number 1, all what I have here digital data, 1010 digital data. Okay. So now if I need to design what we call an encoder. So the input of this encoder is actually digital data. The output is actually digital signal, voltage. So the input 1 and 0, the output is voltage. Okay. For sure, we have different ways to do it. We have different ways to do this encoding. Here we have decoder. So this decoder should receive a digital signal and it has to convert it to digital data. Okay? And again, this is just a very easy example here. I assume we have 2 levels. But actually, as you will see, this digital signal, we may have more than 2 levels, Again, so again, that's what I'm going to explain now. But here, I'm explaining encoder and decoder. Any questions? Okay. So actually, here, I'm going to explain many ideas for this one. Maybe you are already familiar with some of them, like unipolar, polar, non-return to zero, Manchester, differential Manchester, bipolar, multi-level, multi-transition. So all of them are doing the same thing. All of them should convert the binary data to digital or to the digital data to the digital signals. So what is important now, how I can tell if an encoder, if this is a good encoder or bad encoder. You get what I'm saying? So all of them are encoders. How I can evaluate them? How I can tell this is good, this is bad, this is good, this is bad? How I can tell? There should be some metrics, right? Or let me say it in other words. In other words, if I have a very wonderful encoder, how it should look like? How good encoder look like? And then when I teach this one, we're going to do the comparison, and then we're going to tell you this is good or bad. You get what I'm saying? And so on. So that's what I'm going to do in the beginning here. So in the beginning, I'm going to teach if I have a good encoder, how it looks like the good encoder, what metrics we are going to have here. So for sure, I'm going to give you details, but the first metric is the bandwidth or what we call signal rate or bandwidth and bit rate. Okay, so for sure, I'm going to give you details now, but you should, that's what I explained before, and that's you should understand. Usually what we want to do in communication, I want to maximize the bit rate. That's for sure. You got what I'm saying? I want to maximize the bit rate. At the same time, I want to minimize the bandwidth because the bandwidth is the cost. Okay? Or let's say it, or I can say it in a different way. Given a certain bandwidth, you're going to ask, bandwidth is the overhead or the cost, or this is what resources. The network is going to give you a bandwidth. Given this bandwidth, how I can maximize the bit rate. Okay? So for sure, if I have 2 encoders, one encoder has higher bit rates given the same bandwidth. So for sure, this encoder is going to be better here. You got what I'm saying? So yes, we have different encoders. Every one of them is going to give me different bit rate. Yes, the higher the bit rate, the better the encoder. Okay, that's okay. I'm going to give you details, but I'm going to give you just a big picture now. I have other things. As I'm going to explain, we have something we call DC component. We have baseline wandering. Okay. We have synchronization. We have complexity, built-in error detection, immunity to noise. You got what I'm saying? So I put some guidelines. I put some metrics now for sure in order to be able to evaluate the encoders. So before I start teaching the encoder, we should understand how good encoder is. The interesting part, and that's what you will see. There is no way I can do good in all of these. You got what I'm saying? So for example, I wanna get high. I wanna get high bit rate. Okay. Also, but usually you have to pay a cost for that. It's not for free. It has to be more complex. I have to do some sacrifice. You got what I'm saying? I can't for sure. I wish if I can do all of them are good, but it's not the reality. The reality is you have to do some sacrifice. Okay. So for example, if you wanna improve, that's what you are gonna see for sure. If you wanna remove the DC component because that's a problem, as I'm gonna explain right now, what is this? Or you wanna have self-synchronization, you have to pay the price for this one. Okay. Anyway, so again, we wish if you can do well in all of them, but that's impossible. You have to do some sacrifice. Anyway, so let's start with the very beginning here. In the very beginning, I want to make just a very, very quick definition. Okay. Here, the first definition is what we call data element and signal element. So this is a very definition. What do you mean by data element? Data element, you know the data is digital 1 and 0. Data element is actually the smallest entry represented a piece of information, which is a bit. So data entry means data element means a bit, 1 bit. So 1 bit, the smallest piece of information, which is 1 bit. Okay. Signal element is actually the shortest unit of time of the digital signal. Okay. So let me look at this one. You will understand better here. So try to see what I mean. So this is the data for sure. Always the data element is only 1 bit. Okay. Signal element. This is the signal element. This is another signal element. This is another signal element. Okay. So signal element is related to the signal. Okay. As you see here. And also, so here in this case, we have also another important parameter. This parameter, we call it R. You will understand why this one is important. So R actually is the number, how many, the number of data element divided by the number of signal element. So for example, here in this case, R is equal to 1. Why? Because it's actually here R is equal. We are gonna transmit 1 bit using one signal element, 1 by 1, which is 1. Okay. Let's see another case to understand better what is the difference between data element and the signal element. So here, as you see here, this is one data element. 0 can be 0 or 1. Okay. But here, this one element is going to be actually transmitted using 2 signal elements. This way. You will understand. Okay, someone can ask me, so why I have to do this way? Why I have to make this transition here? You see what I did here? Why I have to do it? Okay, you will understand later why you will need to do something like that in order to improve synchronization. Okay, so there is a reason, but I'm going to explain later why. But anyway, let's focus now on what is data element, what is the signal element, how can you calculate R? And now we need to know the bigger R is better or the smaller R is better. We need to know that. Okay, just let me finish this part. So here, if you look here, every data element is carried by, or in order to transmit one data element, so actually I need 2 signal element, as you see here. So as in this case should be 1/2 R. Okay, let's see another case. Another case here in case of multi-level. In case of multi-level. So here in every level, I can transmit more than 1 bit in case of multi-level. Right? In case of two levels, so here in every level, we're going to transmit 0 or 1. Okay, so here you can see here, here we have 2 data elements, as you see here, 2 data elements carried by only 1 signal element. So R is equal to 2. You got what I'm saying? So if you look at this one here, this signal here, we have 4 elements because every bit is 1 element. So 4 elements. So in these 4 elements are going to be actually transmitted by 3 segments. So it should be 4 divided by 3. in the textbook, they give us like analogy, a very interesting analogy. I want to explain this analogy to you to better understand what we're doing here. The analogy is, again, R is actually number of data elements divided by signal elements. Okay, so the analogy here is like in transportation. In the transportation, you can see the data element is like passengers, okay? And you can see the signal element like the vehicles, okay? So what I want to do is, I want to try to transfer as many people as possible using a small number of vehicles as possible. You got what I'm saying? So actually, by this analogy, you can tell that the bigger the R, when R bigger, what it means? The bigger the R, that means I can transfer too much information using a small number of signals with something very good. You got what I'm saying? And later, when I give you a formula for the bandwidth, you will see that there is a relation between a bit rate and the R. Okay, you can see the bigger is the R, I can increase the bit rate this way, and it makes sense. Okay, so you can see this like a car. In this car, I'm gonna put 2 people in 1 car. Okay, that's why R is equal to 2. So every car is gonna take 2 people, right? Here, every car is gonna take one people. Okay, so I want to transfer as much data as possible. Okay, using as a small signal element as possible. Yes, you have a question here? Okay, thanks. Okay, so now again, all what I did here, you should understand what I mean by data element, which is just 1 bit. You should understand what I mean by signal element. Okay, you should understand signal element like a cost. This is the cost, like how many cars I have. This is the signal. So we try to and for sure it's we try to transfer as much data element as possible using as a small number of signal element as possible. And this can be reflected by R. You got them. If R equal to 1, that means I'm going to transfer 1 bit using 1 car. Car here in this case, 1 signal element. You got what I'm saying? If R is half, is for sure this worse than this one. Okay. And you will see it in the bit rate. Okay, you will see here the bit rate here. The bit rate here is going to be half the bit rate here. Makes sense, because here, using 1 signal element, I'm going to transfer 1 bit. Here, I need 2 signal elements to transfer 1 bit. So the bit rate here is going to be half the bit rate here, which is bad. But again, and this is an interesting part, again, we cannot do good in all of them. We wish if we can, right? So here, maybe I lost half of the bit rate from here to here, but as you will see later, maybe this one is going to be better regarding synchronization, regarding other metrics. You got what I'm saying? So you can find some metrics are good, some metrics are bad, and so you will see. But now let's focus on this one. Okay. And now I want to get a formula here. So you should understand the difference between data rate, signal rate, and bandwidth. Okay. Data rate is actually, that's what we call N. That's what I explained to you before. This is how, this is the number of data element, which is actually number of bits. Every data element is 1 bit. So actually, the number of bits sent in 1 second, in bit per second. Okay. This is for sure. This is what I want to maximize. Okay. Also, we have another thing, we call it signal rate. Signal rate. This is actually how many signals I need in 1 second, and the unit of this one is in baud. Okay, and this is actually proportional to the bandwidth, or this one can reflect the bandwidth. Okay, so here our goal in data communication, we want to increase the data rate while given the same amount of signal rate, how I can maximize the data rate. You got what I'm saying? Anyway, there is a formula, and that's what you should see now. There is a formula between signal rate. So signal, again, signal rate is actually, it is like bandwidth. So this is the relation is here. The relation is the signal rate. Again, I told you this one is, we measure it in baud. Okay, and this one can tell you how many signal elements you need, how many cores you need. Okay, how many signal. So this is the relation here. C is constant value. Most of the times this C is half, okay, but it's a constant value. And then N is the bit rate, okay, and then 1 over R, okay. So you can see here what I have just said right now. I told you before, the bigger the R, what it means. When R is bigger, what it means? It means I was able to transfer many passengers using a small number of cars, which is good, right? So here, the bigger of the R, so you will find, as R is bigger, you will find this term is going to be small. That means I'm gonna need a very little bandwidth from the network, which is good. You got what I'm saying? Or you can flip it. You can say N is equal bandwidth. S is here is the bandwidth, okay, divided by 1 over C times R. Okay, so I just put here. I just put in one side and the other terms in the other sides. Okay. So you can see here, it's very clear here, given a certain bandwidth, okay? So the higher R, the higher the bit rate you can get, okay? So very important relation, we're gonna use it all the time. You will see now, this one, the value of N or the value of S is actually how much bandwidth you need from the network, right? This one is going to be different from one encoder to another, as you will see when I teach them. For example, you will see here that, for example, here I'm going to tell you the bandwidth is N divided by 2. Okay. For another one, it's N divided by 2, and that's good. For another one, it's N. It's double the bandwidth. So this in bandwidth, this one is worse, but maybe it's going to good in other things. That's what we're going to explain. So one of the metrics, one of the important metrics we're going to explain for every encoder, I need to know how much bandwidth you need for me. Okay, for the same bit rate, or in other words, it's the same thing, by the way. In other words, given a certain bandwidth, what is the bit rate? What is the bit rate given the set? Okay, so if I tell you, given the same bandwidth, okay, this encoder is going to give you more bit rate, which is good. In other words, I'm going to say for the same bit rate, this encoder is going to ask for a smaller bandwidth, which is good. It's the same thing, okay? So anyway, so here, this is the formula we're going to use. We have here. Yeah, sure. Yeah. No, the ratio. What's important is the ratio. What's important? Okay, let me tell you here. Okay, here you can see, you can imagine every signal element like one car. Okay, here I'm gonna transfer one person using 2 cars, for example. You got what I'm saying? So spade. Here I'm gonna transfer two bits using only 1 car. You got what I'm saying? So this one is better. So that's why we have to look at the ratio. So here's the ratio. R is equal to 1. R is equal to half. R is equal to 4 divided by 3. R here is equal to 2. So which one is the best here? For sure, this one is the best. R is equal to 2. That means I can transfer using only 1 car. I can transfer two bits. You get what I'm saying? But for sure, this is it's somehow tricky because there are many factors here. Okay. So actually, these 2 are multi-level. And multi-level is more complex than 2 levels. So here, this part here, we have only 2 levels. We have 2 voltages here. Here we have multi-level. Usually in multi-level, we have higher bit rate. Okay, but there is a cost. The cost is going to be too complicated for the receiver. The receiver has to be more complicated to differentiate between the different frequencies we have here. You got what I'm saying? So anyway, so we're going to use this formula all the time. Okay. So C is actually a constant. Most of the time it is half. It's equal to half. So here I just will give you a very straightforward example here. In this example, you have here, I give you R. Here I'm telling you a signal is carrying data in which one element is encoded in one signal element. R is equal to 1. So here every data element is encoded in one signal element. R is equal to 1. And then I give you here, bit rate is 100 kilobit per second. This is in here, okay, the bit rate. Also here, I tell you R is, I already give you R is 1, and C always have. So now I want to calculate the bandwidth. So you'll find S here, which is the bandwidth, is going to be 50 kbud. So actually here, so give it, so in this scenario, if I want to, given this scenario, if I want to get 100 kilobit per second, the bandwidth has to be 50, okay? So in other words, the bit rate, which is in, actually it should equal to the bandwidth. Okay, this is, we had this formula before, if you remember. So this is exactly the same thing. So here in, this is in, the bit rate is actually double the bandwidth. And this is the best thing you can do in 2 levels. So in case of 2 levels, the best bit rate you can get is the double the bandwidth. That's what I explained before. Okay, this is the best thing you can do here. Yeah. Okay, so now I want to move to the next. So again, every time I teach encoder, I'm going to tell you what is the bandwidth. Okay, that's what you will see later. You will see here always I give you the bandwidth. You should keep in mind the lower the bandwidth, for sure is the better. You can, so for the same bit rate, I need a small amount of bandwidth. Is going to be better. Okay, this is a metric I'm going to use between different encoders. The next thing here we have something we call it a DC component. We have baseline wandering. We have self-synchronization, so let me explain what I mean by this before, because this also one of the metrics I'm going to use to evaluate the different encoders we have. Okay, it's very simple. So let me explain it. Okay, so when you transmit a signal this way, this is at the sender side. Okay, for example 1 0 1 0 1 0. Okay, at the receiver side, to receive the same signal, what I need 2 things. Number 1, I need to identify the boundary of each bit. So I have to know this is for 1 bit, this is another bit, and so on. So both of us, we have to use the same boundary. You get what I'm saying? So boundary means this is from here to at the same. So this is one thing. Okay, if both of us, 2 things, in order to receive the same signal you transmitted, number 1, the receiver and the sender, they have to use the same boundary here. Okay, this is number 1. Number 2, I have the voltage, because once I receive a voltage, I have to decide if this voltage is 1 or 0. You get what I'm saying? So number 2, I should be able to identify the voltage or differentiate between 1 and 0, the voltage of 1 and 0. Okay, so 2 things here. So let's start with the first one. The first one is the boundary. So we have to be synchronized. So what synchronized means? It means synchronized means if this is a bit here, okay, so synchronized means if this is the sender, okay, so here at the receiver, I'm going to be exactly at the same time. Okay, so this is 1 bit for me, this is also 1 bit, this is 1 bit. So we are synchronized. Is that okay? Okay, this is what should be. If we are not synchronized, what problem it can happen? I'm going to receive wrong data. How? I'm going to tell you how. So that's what we call lack of synchronization. If we are not synchronized, for example, here, this is the time, as you see here, this is the time for 1 bit. But at the receiver time, this is a time for 1 bit, as you see here. So what happens when if you transmit this signal, I'm gonna receive a completely different signal, because here I'm gonna consider this is the time for 1 bit, 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 but actually what you see was different. So for the same signal here, I'm gonna receive here 1, 1, 0. So look here, you transmitted 1, 0, 1, 1, 0, 0, 0, 1. But what I'm gonna receive is, because we don't have exactly the same duration, it's not exactly the same duration, or it's maybe shifted. It's not gonna start exactly at the same time. So two things, it has to be the same duration, and also it has to be synchronized, means at the same time. If it is shifted, you are going to transmit something, I'm going to receive something else. And that's what happened here. So if you see here I'm assuming it's going to be the bit duration is different. So what happened here? You sent this signal. So here I'm going to read it like 1 and 1. Okay. And then here I'm going to 0 and then 1, 1. So look, so this is a message you transmitted. And because of lack of synchronization, this is a message I'm going to receive. You got what I'm saying? Quickly for 1 minute before I end this lecture. So why we suffer of lack of synchronization? What is the reason of that? I'm going to tell you why. Very simple. So at the center and the receiver, actually, we are going to use an electronic circuit to generate a clock, what we call a clock. Here also we have a clock, what we generate a clock. Is that okay? So here, actually, no matter, or it's going to be very difficult to generate exactly the same clock. This is something normal. This is because the circuit has electronic component like capacitor, it has a crystal and these things. And there is no way to get exactly same values. Also aging. So, or temperature has some impact on that. So because all of this, what happens is what we call clock drift. So it's maybe very difficult to generate exactly the same clock. So it's normal that we are not synchronized. You got what I'm saying? This is something normal. Okay. Even if we try to generate exactly the same signal, it's going to be too difficult to be exactly the same thing. Okay. Because of many not natural factors like temperature, like component are not, if you have a resistance, it's not going to be exactly the same value. There are a lot of variation in the electronic devices. Okay. So again, conclusion, lack of synchronization, something normal, it can happen. Because of lack of synchronization, you are going to receive wrong data. You are going to receive wrong data. So how can we solve this problem? The way we are going to solve this problem is, I'm going to put some information in the message I'm going to transmit to help you to synchronize with me. You got what I'm saying? So when I transmit a message, I will do my best to put something in the message that's going to help you. If you lose synchronization, you're going to resynchronize. How can we do that? Very simple. For example, here, you can do something like that. So that if you lose synchronization, you can use this edge, the transition. Every time there is a transition, if there is a transmission, you are going to tell the other side, if you didn't do the transition here, you have to shift it here. Anyway, so that's enough for today. Oh, we need to do that thing. Uh, 8288. So 8288. 8. Oops, what's going on? Thanks. 8288.